Okay, so this is part 2 of the responses to exercise, the acute ones. Remember what acute is? They're the ones that happen in the short term. Okay, there's the same learning intention. You're going to be able to recall at least 3 of the acute responses. Okay, so respiratory, cardiovascular, and muscular, any one of those. So, like I said, looking specifically at the cardiovascular. So we're looking at the heart, and we're also looking at the veins, the arteries, the capillaries, so on and so forth. Cardiovascular system is responsible for keeping us alive, partly. Okay, we've also got the respiratory side of things, but these are the hoses that the blood and everything flows through. Okay, it needs to maintain a constant supply of blood to all parts of the body, the brain especially, the lungs, the muscles. Okay, but during exercise, that need increases. And there's a number of changes that the cardiovascular system, or CVS, undergoes. I was just too lazy and I didn't want to write cardiovascular system. So our cardiac output, or Q, don't ask me why it's Q. CO is, CO2 is carbon dioxide. So that would probably why it's not CO. Ask your science teachers. I don't know. So it's a combination of stroke volume and heart rate. Okay, so it's the amount of blood that's pumped out of the heart every minute in liters. Okay, the formula, really easy. Q equals SV times HR. All right, remember that formula. So let's look at a table. Okay, table on page 146. So we've got our trained and we've got our untrained athletes. At rest, the average stroke volume, so that's one beat. Okay, that's one pump of the left ventricle out into the body is going to be 75 milliliters per beat. At maximal exercise, it's going to be 112. But then you look at the trained athlete and he's got a stroke volume of 105. And at maximal, he's 126. So he's getting another, at maximal exercise, I can't even speak tonight. He's getting, you do the math, another, what is that, 14 milliliters of blood. Okay, that's I've screwed it up. I've lost my train of thought. Okay, so anyway, he's getting an extra 14 milliliters of blood at maximal exercise. So that means that his heart doesn't have to work anywhere near as hard. If you look at this, he's got a heart rate at maximal exercise of 192 compared to this person here who has 200 beats per minute. And then finally, his cardiac output is going to be a lot more. When we say a lot more, I mean it's 2 liters, but 2 liters is still a fair bit in terms of like how much blood is being pumped around the body. That was a terrible, terrible slide, and you should just forget it forever. Don't forget the, concepts about the untrained and trained, but that was terrible. Sorry. Okay, let's try this again. Stroke volume. With exercise, the heart's going to increase its beats per minute, okay? There's more need for more blood, more oxygen to be pumped around the body. So the heart, it has to increase. That means that the cardiac output, or Q, is going to increase at the same time. Okay, so stroke volume is the amount of blood ejected from the heart in one beat. So the left ventricle, boom, that's stroke volume. Okay, during rest, the contractions of the left ventricle are weaker and it increases during activity, which means...
What is stroke volume? Stroke volume is the amount of blood ejected from the left ventricle of the heart in a single heart contraction. It is the measurement of the difference in the amount of the blood in the ventricle before a contraction, called end diastolic volume, and after a contraction, called end systolic volume. SV equals EDV minus ESV. So for example, if the ventricle has 144 milliliters of blood in it before a contraction and 50 milliliters after a contraction, the stroke volume would be 94 milliliters. It's estimated that the average stroke volume ranges between 50 and 70 milliliters at rest and 110 to 130 during exercise. Elite athletes are estimated to be between 90 and 110 milliliters at rest and a whopping 150 to 220 milliliters during cardio training. Men in general have larger stroke volumes than women because of a larger sized heart, and individuals who are fit also have a larger stroke volume. So for instance, let's say we have two ladies that are both around the same size and age, but Katie here works out regularly and Jessica here does not. Both are required to walk a mile
Jessica's
at a relatively fast pace. During each of their walks, we would see that Jessica's heart rate would be higher than Katie's. This is in part because Katie does work out regularly, so her stroke volume is greater. She is pumping more blood to her muscles with each heartbeat than Jessica is. At the end of their walks, we may find that both ladies have pumped the exact same amount of blood, but Katie has done it with far fewer beats of the heart. There is a point where stroke volume of the heart maxes out. At a very high heartbeat, stroke volume may actually decrease due to the shortening of time for the heart to fill with blood. And that be the basics on stroke volume of the heart.
I hope that made sense. So your heart rate, I don't need to explain what it is. You know what it is. It's the number of times your heart beats per minute. Really easy. Okay. It's also the most important factor when you're trying to work out what your cardiac output is. Okay. Submaximal exercise, your heart rate increases until the demands of the activity are met, which is steady state. Okay, we've talked about that briefly with the energy systems video previously. So your heart rate will keep going up and up and up and up and up until it gets to that point where it's like, hey, I've got enough oxygen, I don't need any more. I'm just going to keep at that sort of rate until it increases again, or the activity stops and then it'll go down. So what we have here in our little table, picture, whatever you want to call it, are the different exercise zones for differing ages. So if you look at myself, for example, I'm going to fall roughly here, which is kind of depressing. Okay, so my maximum effort, my heart is going to be beating at 180 beats per minute. For any sort of cardio training, I should be aiming to get my heart around that sort of that 126 to 144 beats per minute. You guys are obviously going to be a lot lower. You're going to be somewhere down here. So you're not even on the chart. You don't have to worry about that. So you can see as age increases, the maximum heart rate decreases. To calculate your age, please don't forget this formula. It's 220 minus your age. I don't know why, but some people still manage to get it all confused and mixed up, and they just make up some, BS, and it's not that hard. It's 220 minus your age. Okay, so if you're 20 years old, your maximum heart rate is going to be 200. This is something that confuses people a little bit. Okay, we've got Arterio-Venous Difference, or AVO2 diff, and our oxygen consumption, which is the VO2. Don't get the two terms confused, okay? AVO2 diff is the difference in oxygen concentration between the arteries and the veins after the muscles have taken out what they need. VO2, or VO2 max, is the total amount of oxygen that the body consumes. It's the volume of oxygen that the body can consume, the maximum amount. So don't get those two terms confused. Okay, so like I said, AVO2, it's the difference in the amount of blood between the arteries and the veins. So from here to here. Okay, so the muscle's taken out what it needs, then there's obviously a bit of a difference. At rest, we use less oxygen, so the majority goes back to the heart. But at exercise, more oxygen is extracted from the arteries by the muscles, which gives us our AVO2 difference. So if we look at the example there, and I'll come back to the VO2 in a minute, if we look at the little diagram to the right, okay, we've got 20 milliliters of oxygen in the arterial blood, 20 mils per 100 mils, okay? After it's passed through the muscle, the oxygen has dropped, okay? So there's now 14 mils per 100 milliliters, which means our AVO2 diff, you work out by taking the arteries minus the veins, gives us our 6. So our AVO2 difference is 6 milliliters of blood per 100 mils. Okay, so at rest, you would expect to see that increase. Okay, the VO2 is the amount of oxygen that can be consumed during exercise. Okay, so you've heard the term VO2 max. We'll look at videos, we'll look at some examples of VO2 max tests. I have one that I can show you. But that is the maximum amount of oxygen that can be consumed during exercise.
The next concept we're going to look at is the arteriovenous oxygen difference. Now, this sounds like a really complicated thing. There's some big words getting around in here. But what we're talking about is the difference in the amount of oxygen that's in this blood here, the arterial blood that's going to the muscles, as opposed to the volume of oxygen in this blood in the venous system going back to the heart, so from the muscles. So what we've got here, if I was to take 100 mils of blood out of your arteries and arterioles, I would get a certain concentration, and that's what I'm sort of indicating here with my little dots. There's a certain certain concentration of oxygen in that blood. And then if we were to do the same thing and take 100 mils out of your venous system, out of your veins and venules, we would find that the concentration of oxygen is less. Okay. Now what that's indicating is something is going on in the middle here. Something is happening at the muscle itself. And that, of course, is oxygen uptake. So what's happening is this arterial blood is entering the muscle. The muscle is taking out the oxygen that it wants, uptake, and then anything that wasn't used is sent back in the venous system. We call it deoxygenated blood. In other words, there's less oxygen in it than there was up here in the arterial blood. And the difference between the two becomes the AVO2 difference. Okay, so to put some numbers on it, let's just say at rest, 20 mils of oxygen per 100 mils of blood were sent to the muscles and 15.5 returned, then the difference would be 4.5, 20 minus 15.5. But let's say we start exercising, that 20 mils might become more like 12 mils now going back, not 15.5. So the difference now is 8. In other words, more was taken by the muscles. Okay, so the greater the AVO2 difference, the greater the volume of oxygen that the muscles actually uptake. Okay, and as intensity goes up, we'd expect the AVO2 difference to do exactly the same because the muscle needs more oxygen, it takes more oxygen.
That was pretty much what I said. I hope he just explained it a little bit better than what I did. Moving on. So venous return. Venous return is the amount of blood that is returned to the hearts. Okay, veins obviously take the blood back to the heart. Okay, it needs to increase during exercise because the muscles are demanding more oxygen, so there's going to be more blood that's being circulated around the body. 3 ways that it happens: the muscle pump, the respiratory pump, and the constriction of veins. Okay, so veins work a little bit differently. They don't have the same amount of pressure pushing the blood through. So what they have is these little veins. They have these little flappy things that, as the blood flows through, they open up. Okay, so the blood flows through, and then when the blood puts pressure back on the veins, so when it tries to flow backwards, they're like those gates at Coles and Safeways that are really annoying. They shut, and then you can't get out. Okay, so the same sort of principle with the veins. The respiratory pump is kind of similar to the muscle pump. So basically what happens with the muscle pump and the constriction of the veins is it's called the skeletal muscle pump. I'm going to cover these two sort of in the same sort of way. The respiratory muscle pump works on pressure. So you breathe in and the diaphragm goes down, okay, and that increase in chest cavity pressure forces the blood out and back up to your heart. Okay, when you breathe in, the opposite happens. There's a decrease in pressure and the blood flows back down. Okay, so that cycle keeps the blood pumping around. Whereas the muscle pump, it's kind of a similar sort of thing, except it's using the muscles to basically crush the veins. And this is where the valves come in handy as well, because like I said initially, the veins don't have the same amount of pressure as the arteries do. So what the veins rely on is they rely on those little valves, those stupid little gates that stop you from walking back through when you realize you don't want to go into Safeways or Coles or any of that. They rely on those valves, and it also relies on just you being physically active, walking around, moving an arm, moving a leg, whatever it is, because those muscular contractions are going to squeeze the blood along. It's like, when you have the Zupa Dupas and you're trying to get the ice block or the icy pole part out of the plastic tube, you keep squeezing along further and further and further until you get to the icy pole. Same sort of idea. So we have our distribution of blood flow. So during exercise, okay, this is how, this is what it sort of looks like. Okay, we've got our internal organs at rest, getting about 50–60% of the blood. Excuse me, that was dinner. Then when we start exercising, something happens. Okay, the blood gets diverted away from the internal organs and the other tissue, the skin and that sort of stuff, and it starts going towards the skeletal muscle. And you can see the difference at maximal exercise. 88% of the blood is going to the skeletal muscle, and then the brain, the skin, the heart, they get the leftovers. So vasoconstriction and vasodilation.
Vasoconstriction for dummies.
Not
Let's
that you're
look at the word
dummies.
vasoconstriction. If we get rid of the constriction, we get the word vaso.
Such a dirty
Vaso
word.
basically means vessel. In this case, it refers to a blood vessel. The word constriction means to draw or press in, to cause to contract or shrink, or to compress. Therefore, the word vasoconstriction means when blood vessels constrict or get smaller. But why does vasoconstriction occur? Vasoconstriction is part of a much larger bodily system called thermoregulation. Human beings are warm-blooded organisms, meaning we need to keep our body temperature the same for our body to work. Thermoregulation is the process by which our body maintains its normal body temperature, which is approximately 37 degrees Celsius. It does this through sweating, shivering, vasodilation, and vasoconstriction. Vasoconstriction occurs when the temperature outside the body is colder than 37 degrees, so the body needs to keep warm in order to keep working. So how does vasoconstriction work? In this example, let's make the train track the blood vessels, and the train the blood travelling through it. The blood travels down the vessel until it reaches the surface of the skin. When it reaches the edge of the vessel, the heat in the blood is lost through the skin, making the blood colder. The cold blood then travels back through the peripheral vessel and back into the body. If our body did nothing, our blood would get too cold and our bodies would shut down.
So you become hypothermic. Hypothermic.
When the
Sorry.
temperature outside is colder than the body temperature, the brain releases a hormone called adrenaline. The adrenaline travels to a small peripheral blood vessels near the surface of the skin. The adrenaline causes the peripheral blood vessels to constrict, limiting the blood flow to the surface of the skin. Most of the blood is then redirected along shunt vessels, which connect parallel peripheral vessels. This means the blood doesn't travel as close to the cold outside environment on the surface of the skin, and therefore loses less heat.
And
So
keeps
that's
us warmer.
basically vasoconstriction in a nutshell.
Come on, wrap it up. That's where I got my resources from too. So, like you said, vaso meaning vessels. Okay, constriction meaning to restrict, dilation meaning to make more open. Okay, so the vasodilation or vasodilation, however you want to say it, would be the opposite. Would be the opposite, where the if we're using the train track example, the blood would be diverted. Instead of going through the shunt vessels, it would go around to the periphery and the exchange of heat would happen and the body would be cooled. Blood pressure. I'm sure you've heard the term before, but you might not know what it actually is. So it's the force that is exerted against the walls of the blood vessels. So every time your heart beats, okay, there is pressure that's exerted against the walls of the arteries and the veins and that sort of thing. It's like you know, your garden hose when you kink the hose, or even like the maybe you've got one of those shower heads that you can pull off and, you know, use the shower head. I do, that's why I'm talking about it. If you don't, you're missing out. But when I turn the shower on, yes, I do shower, the hose that attaches basically the outlet of the shower where the plumbing leaves the house and goes to the shower head, you can see that it actually becomes a lot firmer. And then the opposite happens when you turn the shower off and the water is no longer flowing. It becomes quite loose and flaccid. There you go. There's something for you to have a laugh about. I am racist. I'm talking about flaccid and stiff. Did I mention stiff? I can't remember. Anyway, getting sidetracked. So there's two phases. There's a contracting, there's a relaxing. So systole is when the heart is contracting. Okay, so it's pumping the blood out. It's squeezing the blood out. That's systole. Okay, then you have diastole or diastole, depends on how you want to say it, is when the heart is relaxed. So it's just pumped the blood out of the ventricle and it's starting to fill again. That is pretty much blood pressure. What I was going to do is show you a picture of my forehead. I have a little, this is my little boy's fitness trackers. The normal resting blood pressure should be about 120/80. Okay, so what we're going to do is we're going to take my blood pressure. Seems to be reasonably accurate. Let's take my blood pressure. Waiting. My blood pressure currently is 102/73. Just out of curiosity, let's do my heart rate. Let's see what that comes back as. I don't know whether you can see that. Yeah, not really. I'll have to show you once it's read it. My resting heart rate is 60, was 64, it's gone up to 60, no, there we go, 63, yes, it's going down because it's not even recording my heart rate. So it was 65 beats per minute. The average resting heart rate is about 70-ish. So by the time the blood reaches the capillaries, it's lower than when it was ejected from the aorta. Okay, the capillaries are like the very, very bottom end. It's like you're going to get more pressure coming out of the outlet when you turn the tap on, turn it on flat out, and it's pouring water everywhere. You know, your boots are getting soaked, everything like that. And then you hook up, or let's say 50, 60 meters of hose. By the time all that water has flowed through that 60 meters of hose and it gets to the end where you're trying to water your plants in your garden, you'll probably find that it's going to be a trickle. Whereas if you had less hose, then there'd be more pressure. Okay, so by the time the blood reaches the capillaries, which is like the end of the hose, it's going to have a lot less pressure. So we use a device called a sphygmomanometer. I dare you to try and say that, and I bet you're trying to say it right now. And that was what I just used to take my blood pressure. They used to have, and I mean they still do have, like you can see in the picture there, the digital blood pressure monitors. I have one at school, and I would have done the prac with you guys. We would have taken your blood pressure and just seen, you know, where it was at and so on and so forth. You also have the big ones that look like thermometers. So they actually have mercury within them, and it's measured in mmHg, which stands for millimeters of mercury. So basically what happens is it's the time for, I'm going back to my uni days. I haven't talked about this for a while now, but we did a prac where we actually recorded our blood pressure the manual way. So you would squeeze the cuff and you would basically measure when I think it was when you stopped hearing the sound of the blood flowing through, and then you slowly release, and then you heard the sound of the blood start flowing through and started moving again. I think that's right. I'm not sure. Don't quote me on it. But you just need to know what the two measurements are. So systole when it's filling, when it's contracting, so when it's emptying, and diastole or diastole when it is relaxing and filling up again. Chapter check questions. So chapter check questions. You are not going to find these in your textbooks. I've taken these from the other textbook, from the Year 11 textbook. So I want you to answer these questions. Number one, what are the major differences between the cardiovascular systems between males and females? Question number two, why does systolic blood pressure show greater increase than diastolic blood pressure during the exercise phase? And question four, what happens to the blood flow, what happens to blood flow to the stomach and muscles if a person has a meal and then goes for a swim? These aren't in your textbook. Pause the video and we'll come back and we'll discuss the answers. So the answers. The major difference between the males and females is that the male has a larger heart. The reason being is because the males have a larger chest cavity. They are generally larger than females as well. Sorry, girls. Systolic blood pressure is the amount of blood ejected from the heart. So this is going to increase during exercise, but the filling basically remains the same. So that's why you would expect to see an increase in the systolic blood pressure. That's the blood as it's being pumped out of the heart. Finally, the last question, question 4, well, question 3. So, same as exercise, but the blood is going to be diverted from the working muscles because they've just eaten food. So the blood's going to go from the working muscles and all those sort of other places that it would normally be to the stomach to help digest the food, which means that there's going to be less available to the muscles, which means that there could potentially be trouble if you were to go for a swim, which is why Mum always said to you, don't eat that food and then go for a swim. You've got to wait for half an hour. Well, my mum did anyway. But do you know what? I think there were times where I was actually eating in the pool, and guess what, Mum? I'm still here. Prac. I can't remember what I wanted you to do for the prac. Let's see. There it is. If you have access to a sphygmomanometer, I would like you to do this. Okay, that's not always possible. If you don't, it doesn't matter. See how you go. Chapter check questions. Can you complete questions 1 and question 4 on page 152? These are actually in your textbook. Once you've finished those, check the answers. Once you've finished them, not before. And I'll see you for the final part, which is the muscular system, the acute adaptations for the muscular system. See ya!